Good day everyone, today we will be presenting H2OPTIMIZED project, the Aurora Hill Integrated Drainage Network, designed to address the severe flooding and drainage issues faced by Aurora Hill community in Baguio City. As you may know, Aurora Hill is frequently impacted by flooding due to poor drainage systems, especially across 23,500 square meter area. This not only poses significant risk to public health, but also damages critical infrastructures such as roads and buildings. To address these challenges, we propose the H2OPTIMIZed solution, a comprehensive stormwater and drainage management system built on fundamental principles of physics to optimize water flow. The system is designed to be both efficient, sustainable, ensuring that stormwater is collected, directed, and disposed effectively. Our drainage network incorporates durable PVC, HDPE, and concrete pipes, strategically placed catch bins, and manholes for water collection and maintenance. The system is powered entirely by gravity, meaning it doesn't require any external energy sources, making it environmental friendly and cost effective. Ultimately, the goal of H2O Optimized is to prevent flooding, protect the area's infrastructure, and ensure safety and well-being of the community. It is designed for long-term reliability and environmental compatibility, creating a resilient and healthier future for Aurora Hill and Baguio City. Now for the next section, it explores the application of fundamental principles of physics in the design of the drainage system by incorporating key concepts from mechanics such as projectile motion, circular motion, work and energy, and Newton's law of motion. The system is optimized for efficient water flow, sediment management, and structural durability. These scientific principles ensure the system performs reliably during heavy rainfall, reducing the risk of flooding and improving the overall effectiveness of drainage infrastructure. The following explanations highlight how each principle contributes to the successful operation of the drainage system. For the first one, it is the projectile motion. The concept of projectile motion is applied to calculate the optimal angle at which water flows from the rooftops into slope gutters. This ensures that the water flows efficiently into catch bins without splashing outside, preventing water damages on surrounding areas and maximizing water collection. For the next one, it is the circular motion. Circular motion principles are used in the design of spiral retention basins, where rotating motion helps sediment settle at the center of the basin. This allows for clearer water to move outward, preventing sediment buildup in the system and enhancing the effectiveness of water filtration before discharge. For the next one, it is the work and energy principles are employed to calculate the efficiency of gravity-fed pipes, which transport stormwater downhill by utilizing gravitational potential energy. The system reduces reliance on external power sources, minimizing the need for pumps and ensuring the energy-efficient drainage solution. Now for the last one, it is Newton's law of motion. Newton's law of motion guided the design of the pipes, basins to ensure they can withstand the forces exerted by fast-moving stormwater during heavy rainfall. The system is engineered to resist the impact of high-velocity water, preventing structural damage and ensuring the system operates safely under extreme conditions.
Measurement shall be detailed and specific using the English and metric system. The scale use shall also be shown. To provide detailed and specific measurements using the both English and metric systems, I will outline the dimensions for the drainage system components in both units. Additionally, I will include a scale for better understanding. For detailed measurements, for main drainage pipes, length is for 300 meters or 984.25 feet. For diameter is 400 to 500 millimeters or 15.75 to 19.69 inches. And for feet is 400 millimeters is equal to 1.31 feet, 500 millimeters is equal to 1.64 feet. For scale, if represented in the scaled blueprint, 1 cm is equal to 1 meter in the metric system, or 1 inch is equal to 1 foot in the English. Secondary drainage pipes. Length is for 500 meters or 1,640.42 feet. Diameter for 300 millimeters or 11.81 inches. In feet, 300 millimeters is equal to 0.98 feet. Scale, using the same scale, 1 cm is equal to 1 meter or 1 inch or 1 foot. For tertiary drainage pipes, length is for 800 meters or 2,624.67 feet, diameter for 150 to 200 millimeters or 5.91 to 787 inches. In feet, 150 millimeters is equal to 0.49 feet, 200 millimeters is equal to 0.66 feet. Scale, for scale representation, 1 cm is equal to 1 meter or 1 inch is equal to 1 foot. For catchment basins, number 10 units. Dimensions, typically rectangular or square with dimensions of 1m times 1m or 39.37 inches times 39.37 inches. In feet, 1 meter is equal to 3.28 feet. Depth, usually around 0.5 meters or 19.69 inches. In feet, 0.5 meters is equal to 1.64 feet. For manholes, number 10 units. Diameter is 600 millimeters or 23.62 inches. In feet, 600 millimeters is equal to 1.27 feet. Depth, typically 1.5 meters or 59.06 inches. In feet, 1.5 meters is equal to 4.92 feet. For total length of pipe system, total length all pipes, main pipes is 300 meters, secondary pipes is for 500 meters, tertiary pipes for 800 meters. Total length in meters is 1,600 meters or 5,249.34 feet. For scale representation for blueprint, the scale in metric units 1 cm on the map is equal to 1 meter of actual distance. In English units, 1 inch on the map is equal to 1 foot of actual distance. For example, the main drainage pipe, which is 300 meters in length, would appear as 30 cm long on the map if using a 1 cm is equal to 1 meter scale. Similarly, the catchment basins 1m times 1m would appear as 1 cm times 1 cm on the map.
A drainage pipe in Aurora Hill are vital for residents' health, safety, and well-being. They prevent flooding, eliminate stagnant water, and reduce disease transmission, ensuring a clean environment, minimizing accidents. By protecting properties and supporting local business, these pipes also promote economic stability. Moreover, they safeguard against water pollution, soil erosion, and ecological imbalance.
A drainage system manages stormwater using a combination of above ground and underground components. Water is collected through grates, ditches, and catch basins in low-lying areas. It then flows through a network of main, secondary, and tertiary pipes designed to handle various flow levels. Gravity helps direct the water downhill towards designated outflow points like natural bodies of water or retention basins. Strategically placed manholes allow for easy inspection and maintenance to ensure the system's long-term functionality. The design also incorporates erosion control measures and minimizes pressure built up to prevent damage. This integrated system effectively collects, directs, and safely disposes of stormwater.
What concern shall it address and how will it benefit in the barangay? This project addresses the recurring issues of flooding, stagnant water, and health risks caused by poor drainage in Aurora Hill. Flooding will be mitigated by collecting stormwater and directing it away from residential and vulnerable areas. By reducing stagnant water, the project minimizes breeding grounds for mosquitoes and other pests, which lowers the risk of waterborne diseases. Proper drainage will also prevent water damage to buildings, roads, and public infrastructure, ensuring their longevity and reducing repair costs. Soil erosion, often caused by uncontrolled surface runoff, will be controlled, preserving the community's landscapes and preventing environmental degradation. And for the barangay, the project promotes a flood-free, healthy, and harmonious environment, protects property, ensures roads remain accessible during heavy rains, and enhances the quality of life in the barangay.
Moving on, the following are the operational and material requirements for the drainage system, starting off with water capacity. The pipes are designed to handle heavy rainfall volumes based on the area's coverage precipitation. For the main pipes, it can handle high flow areas, diameter 400 to 500 millimeters. Secondary pipes, for medium flow, the diameter is 300 millimeters. For the tertiary pipes, for localized collection, the diameter is around 150 to 200 millimeters. On energy or power needs, this system is passive and gravity-driven, relying on the natural slope of the land to direct water downhill. No external power is required for the operation. For the next one, it is the durability and maintenance. It requires durable materials such as reinforced concrete, PVC, or HDPE for pipes and basins. Regular maintenance through manholes and inspection points to ensure unobstructed water flow. For the environmental compatibility, it's designed to prevent erosion and minimize environmental impact by directing water safely to natural outflows without damaging the ecosystem. The drainage system requires careful planning, durable material, and strategic placement to function effectively. The water carrying capacity is tailored to local rainfall conditions, with pipe diameters ranging from 150 millimeters to 500 millimeters depending on the flow requirements. The selection of pipe sizes for the drainage system is based on several key factors, including water flow capacity, the area's topography, the volume of runoff expected, and the specific function of each pipe type in the system. Here's a detailed explanation for each pipe size choice.